Alright, this is example 4. If z equals 1 plus I is a 0 of p of z equals z cubed plus 2z squared minus 6z plus 8, factorise p of z over the complex number field. Alright, so p of z has real coefficients. So by the conjugate root theorem, one minus I is also a root, or a 0. Yep. So that means, therefore, z minus 1 plus I and z minus 1 minus I are both factors. So multiplied together, they're a factor. And so that is equal to z minus 1 squared minus I squared, which is equal to z squared minus 2z plus 1, which is plus 2. Oops, yeah, I'll just make that smaller again. Okay. There we go. Alright, so therefore we can say that z cubed, or p of z, is equal to z cubed plus 2z squared minus 6z plus 8. Alright, and that is equal to now some linear factor multiplied by the quadratic factor. And we can see simply that the first term of the linear factor has to be z, and we need 2 to multiply to give 8, so it's going to be z plus 4 is our linear factor. Alright, so that helps us factorise, but then we need to write it over in factors over the complex field. So it's z plus 4 times z minus 1 plus I times z minus 1 minus I. And there we go. Alright, moving on to example 5. X to the 6 minus 1. So we can factorise this as the difference of two squares, and that's x cubed plus 1 times x cubed minus 1. And we can factorise as difference of two cubes, and sum of two cubes, so that's going to be x plus 1 times x squared minus x plus 1 times x minus 1 times x squared plus x plus 1. Right, we'll do a bit of fast factorising on those quadratic terms. So we've got x plus 1 times x minus a half squared plus root 3 over 2i squared, and x minus 1 times x plus a half squared plus root 3 over 2i squared. Alright, and that becomes, let's put the two real factors first. That becomes x minus a half. Shall I write it like this? X minus 1 minus root 3i on 2 times x minus 1 plus root 3i on 2 times x plus 1 minus root 3i on 2 times x plus, I'm just going to make this over a bit, x plus 1 minus root 3, 1 plus root 3i on 2. Okay. And the next one, z to the 5th plus 16z. Factorise that. Well, you can obviously take a factor of z out, and this becomes z times z to the 4th plus 16. Okay. And we can factorise this as a difference of two squares, which is z squared plus 4i times z squared minus 4i. I should say the sum of two squares, isn't it? And then we can factorise this further. And so z is equal to z squared plus, I should say, sorry, minus I to the root 4i squared times z squared minus root 4i squared. Okay, now you can see here that we really need to figure out the square root of 4i. So I'm just going to move my page across and do that here. The square root of 4i is equal to, we'll label it equal to x plus iy, and we're going to then have to use our previous technique. It's x squared minus y squared plus 2xyi. Alright, and therefore equating real and imaginary parts. We get x squared minus y squared equals 0, and 2xy equals 4. So from this one we get x is equal to plus or minus y, and xy equals 2. Okay, and so therefore we get x is equal to y, which is equal to plus or minus root 2. Okay, and so that means therefore that square root of 4i is equal to plus or minus root 2 plus I root 2. Okay. And therefore we actually need I root 4i. So that's going to become minus plus root 2 minus I root 2. Okay. So we're going to use that now to finish off our factorization. So this is equal to, and I'm just going to move it over to the left a little bit more. This is equal to z times z minus root 2 plus I root 2 times z plus root 2 minus I root 2 times z plus root 2 plus I root 2 times z minus root 2 minus I root 2. Wow,